Okay, people. What do you want to know about the exam? Review sheet. What questions do you have?
Go over to number 2.
If you read it to me.
It's prove. I don't think I can figure out that. I'm pretty sure it's prove the quantity AB squared equals B squared and A squared.
Let me grab my iPad and see if I can pull up the review sheet quicker than you can, but if you get to it before me, let's double check.
Got it. Is if quantity AB squared, AB close parentheses squared equals A squared B squared, then AB equals B.
If A squared B, if AB quantity squared equals A squared B squared, then
AB equals A.
aha. So I want to use if this is true, then we have a commutative operation, right? So suppose AB squared is equal to A squared B squared. We'll do this as a direct proof. Well, the thing on the left is AB, right? AB squared is AB. And the thing on the right is AA, BB. Now, I am making a grammatic assumption here. We are working in a group, right? So if we're in a group, then I know some things about parentheses. What can I do?
You can do A, B, so it would be A in parentheses, B, A in parentheses, B. Equals A, parentheses, A, B, and B.
Associative property. Wonderful. I'm in a group. What else do I know has to work?
Inverse.
I have inverses. So what can I do?
Do D inverse.
So if I do A, B, B inverse, then over here, I'll have A, B inverse. What happens?
B's cancel.
One more time, only this time, do A inverse on the left. Which is what I wanted to show. So yes, I can get there from here. And notice at no point did I use any property other than foundational definitional pieces of what makes up a group. These are the sorts of proofs I will ask you for, most likely. If I'm looking at proofs, I want to look at things where you're just applying nothing esoteric and psychotic. You don't have to remember this obscure, crazy fact on page 27.
How many proofs are on
I haven't written it yet. So 2-ish, maybe 3, if we're lucky. It'll be that many if I really feel sadistic. I haven't written the damn thing yet.
Do you have an idea of how many questions?
Somewhere around 7 or 8, like the review sheet. It's not terribly longer than the review. Originally, this was set as a 50-minute class, so it was designed to be finished in that time. But people scrambled in the 50-minute version, so I made it longer.
So we have the entire class period.
Oh yeah, absolutely. I'm not going to take any time away from you.
The review sheet is a really similar format to the test.
Between that and the homework questions, I don't see any reason to throw something at you that is absolutely out of left field. But I say that, and then people are like, I've never seen this. And then I open the book, and I'm like, it's here. They're like, I didn't read that page. I guarantee you, you will have seen a similar problem to whatever I put on the exam. More questions.
We do part B.
Which one's that?
In parentheses, A, B inverse equals B inverse A inverse.
Right?
Yeah.
By definition, that's true. Right? So if I can find something else so that A, B times stuff is equal to E, inverses are unique, right? So let's do this calculation. What do you do?
You can rearrange the order so it's A inverse times B inverse.
How do I know I can do that? But I don't know that it's an abelian group. I can't rearrange orders unless I know it's abelian.
Then you can rearrange the parentheses to be A, B negative 1, A negative 1.
And then that goes away because that's E. And that's E. Hey, wait a minute. Since inverses are unique, AB times this thing gives me E, AB times this thing gives me E. Therefore, AB inverse must be the same thing as B inverse A inverse. I have to be careful until you tell me or prove somehow, hey, this group is abelian. Then I don't know that I can do those rearrangings. We're used to doing that. But I know that in permutations, that F's things up. So I don't want to do that.
So with that one, you basically just said that everything came out to be the identity.
Right, but then I can, AB has a unique inverse. So the inverse of AB must be the same thing as this. This is exactly the same proof we will use in linear to show that the inverse of a product is the product of the inverses in the other order. Because matrix multiplication is not abelian. I think that's this week. Matrix operations is coming shortly. It really is. Better?
Yeah.
All right.
Could you do number 3?
Which says?
Show U4 equals 1I, negative 1, negative I. Like the squiggly brackets.
Yep, that's our set.
Is a group under multiplication of complex numbers.
Okay.
It's cyclic.
Okay. So I want to show two things.
Or no, ask, is it cyclic?
But does it say show it's a group?
Oh yeah, it does say yes.
So first I need to show it's a group,
Mhm.
and then I need to show it's cyclic. So they're two different, and if it's not cyclic, then I'll know that by trying to show it is. And since it's a small group, I can try and show it directly.
Mhm.
But let's start with the first question, is it a group? Because if it isn't, then I can stop right there. What do I need for a group?
Is it closed?
So let's start there. Point 0. U4 is closed under multiplication and complex numbers. So I need you to prove to me that if you multiply any of those two things, any two of those four things together, you get another one of those four things. The easiest way to do that to me would probably be a table. Let's multiply all possible things together. Fill in all 16 little boxes.
So I got 1, I, -1, -I. And then going down, I got the 1, I, -1, -I.
Okay.
And then I did 1, -I.
Wait a minute. I times I is
Also,
I times I is -1. And then -1 times I is -I. And I times I squared is -1, then the extra negative makes that a +1. -1 times -1 is 1. -1 times -I is +I. -1 times -I is +I. -I times -I. I times I is -1, right? And then I have two more negatives. That's 3 negatives in total. That's -1. I never got anything other than one of the things in my set, right? It's closed. Associative is the long, ugly one, but I get to cheat because I inherit associative because I know complex multiplication is associative. Complex numbers are a group. This is a subgroup. It inherits associativity.
so when we do find that it is a group, then we can say something like that.
Yes. Now, I can only do that when I'm dealing with a set of things where I
So
know
like the real numbers, the natural numbers, all that.
fractions, all of
Yeah.
those, yeah.
Alright.
I don't want to make you reprove this from scratch because it's, 64 different operations and, no, ugly, messy, not good. 2. So I have associative. What's next?
Identity. So then since we know that it's a group and it's under multiplication, we could say that it has the identity because of 1.
But I can actually show, hey, look, if you multiply 1 by any of these things, you get that thing back.
And there's not much more to that. You can just say, yes, it's 1.
Well, I have to be able to show, and since I have all those products up there, I'm good.
You could just say first line of the table. Alright.
If I want to know whether or not every element has an inverse, I need to show for each one. No.
Is this the one that you can base off the table? If the top half, the top right half of the diagonal is symmetric to the bottom left?
That shows me that the operation is commutative, which would show me that this is an abelian group, which I wasn't asked to show, but I now know because all of these non-diagonal things match up. This is abelian, but that wasn't one of my questions. But yes, that part would be in there. But how do I do inverses?
You need the identity, right? So
I need something for each row, that there's a column entry that when I multiply, I get the identity. I need something for each column. There's a row, when I multiply, I get the identity. One is its own inverse. What's i's inverse? Because I multiply, I get 1. Negative 1 is its own inverse. Negative i's inverse is I. It's group.
that's all you have to show for inverses.
Yeah, that every element has an inverse. In this case, there are only 4 things. I can match them up and say, look, here's an inverse, here's an inverse, here's an inverse, here's an inverse. Is it cyclic?
You want to say no because it's a group of 4, or you don't know that yet?
I don't know that yet. There are 2 groups of 4, right?
Yep.
The Z4 group, and that one is cyclic, and the Klein 4 group, and that one's not. So my question is, which is this? I don't know off the top of my head. If I remember the homework problem, we actually did show which one this was, but I don't know if you remember that. What's it mean to be cyclic?
When you do the operation of the group, and it returns back to its first.
So I have to do the operation to something, right? So you pick an element and you see if you can get the whole group. So I have my multiplication table right in front of me. I'll be able to multiply fairly quickly. If you start with 1 and you multiply 1 over and over and over again, what do you get? Well, that doesn't go anywhere, damn it. That's not helpful. So 1 is not a generator. If I did negative 1,
Get 1 and then negative 1, 1, negative 1.
that's not the whole group either. So that's not a generator. What if I did I? The subgroup generated by 1 is just 1. Subgroup generated by negative 1 is just negative 1 and 1. What's the subgroup generated by I?
So negative 1 and then
Well, I got to start with I.
I, and
Then negative 1.
And would it go to positive 1?
Well, no, I got to multiply this by I again. So I get negative I, right?
Yep.
So this is I to the first, this is I squared, this is I cubed, and then negative I times I, that's 1. I have a generator. If I have a generator, it's cyclic. Now, please notice that actually does tell me that this group is related to Z4, not the Klein 4.
For groups that are, when it says like generated functions or cyclic groups can be represented by ABN, is that?
Yes, that's what we just did here. Powers
So
repeated.
does that work for when you're adding groups in like Z10, you're like add, so that's, how does it A to the N represent the addition part?
Because A to the N is the multiplicative notation. We're multiplying over and over. I did use multiplication as the operation here. In Z10, my operation is additive. So instead of writing A to the N, technically I should write A plus A plus A dot 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 N times. Which I would write as NA, but that's kind of weird to think about in modular arithmetic. What's 17 times 4 mod 13? It's ugly. It's easier to think of it as repeated addition, but it's easier to write it as powers. Does it matter how you write it? Not in the slightest. By the way, this is not the only generator. Negative I is also a generator. Negative I times negative I. We did that one. That's negative 1. Negative I times negative 1 is positive I. I times negative I is 1. And that's even more confirmation that this is Z4. This Z4 has 2 generators, 1 and 3. Because they're both relatively prime to 4. We did that yesterday. Sorry, Tuesday. Better?
We do number 1.
Hit me.
Determine whether or not the set M equals the matrix AB and then CD, where AB minus BC equals 1 under the operation of matrix multiplication as a group.
AD minus BC equals 1?
Yeah.
Okay. Advanced warning. I need to know how to do matrix multiplication. Matrix multiplication is dot products. It's just 1 for each row and each column. So let's suppose I have 2 matrices, and I know A1 D1 minus B1 C1 is 1, and A2 D2 minus B2 C2 is also 1. The following is a lot of large, ugly, messy algebra. I need to do the matrix multiplication here. Then I need to do this calculation for that new thing. M1, M2. I have to do row, column. Pick a row in the first matrix. Want to do row 1 or row 2? If I do row 1, I need a column in the second matrix. Column 1? 1, 1 means the answer goes in the first row, first column. Do a dot product. A1, A2 plus B1, C2. Across the row, down the column. And that's in 1, 1. First row, second column would use A1, B1, and then B2, D2. Across the row, down the column. And that's in first row, second column, because those are the pieces we used. Repeat now for the second row. C1, A2, D1, C2. And then second row, second column, C1, B2, D1, D2. Ew. Right? Now I need to know, is this in this set? The only way I know is if I do this times this minus this times this, and I get 1. Bleh. That's nasty looking. So let's see what we can get. Time to distribute a bunch. A1, A2, B2, C1 plus B1, B2, C1, C2. I'm rearranging so the letters are in alphabetical order. In each piece I multiply together. So first inner outer, A1, A2, D1, D2. Last, B1, C2, D1, D2. That's this pair. Minus, now I do it over here. A1, A2, B2, C1. B1, C2, D1, D2. That was the wrong one. I did last instead of the outer inner. I'll just do it whatever order you want. A1, B2, C2, D1, and then A2, B1, C1, D2. That's disgusting. Except something wonderful happens. What wonderful thing happens?
Would the first two terms cancel?
Yep. This one cancels with this one. Not that one. So actually not just the first two, A1, A2, B2, C1, but also B1, C2, D1, D2.
I was looking for that other one up top.
But that leaves me 4 terms. That leaves A1, A2, D1, D2 plus B1, C2, D1, D2 minus A1, B2, C2, D1. Distribute the minus sign. A2, B1, C1, D2. A1, D1 times A2, D2. A1, A2, D1, D2. A1, D1 times B2, C2. A1, D1 times B2, C2. B1, C1 times A2, D2. B1, C1 times A2, D2. B1, C1 times B2, C2. Holy crap. Well, it does help if I copy down the right things. That should be that one. This is the same thing you get if you multiply those two equations at the top of the screen together, which means this can be factored. It doesn't look like it, but it actually does factor. It factors into that, which is 1 times 1, which is 1. Holy crap, this is closed. I did say it was painful, messy algebra, didn't I? There is a nicer property in linear algebra called a determinant. What you have just shown is that two matrices whose determinant is each one, their product also has a determinant. Determinant is a multiplicative property. If you already learned that rule from linear, you could just quote it.
I was gonna ask, can we just use what we know about invertibility to prove all these?
If you have taken linear and know that fact, yes.
Sweet.
If you are in linear and don't know that fact yet, well, damn it.
So then, what would it look like if we have taken linear and could use?
A, B, C, D, the determinant of this matrix is AD minus BC. So the other way of writing M, our set, is the set of matrices whose determinant is 1. Right? Now here's the magic theorem from linear, and it says for any n by n matrices A and B, the determinant of the product is the product of the determinants. And that means that the two matrices I came up with, their determinant is 1 times 1. Which is back in our set, isn't it?
Yeah.
2 lines. Officially on paper, linear is a prereq for this course, not a code. Which is why a lot of these examples are linear examples. But I know if I did that to a bunch of people, you wouldn't be able to graduate on time. That's why I'm teaching you this as we go along. It's closed. Matrix multiplication is associative. Property from linear. Is there an identity? Is it in our set? The identity matrix I looks like this. If you do ADBC, then you get 1 minus 0. So there is an identity and it is in our set. How do I get inverses?
You put the original matrix in the matrix with, so you put, yeah, and a line and 1, 0, 0, 1, and you got to do the matrix operations to send it over. That's all.
Row reduction, row operate. You're looking at me like I've lost my damn mind. I don't remember this. Okay, or I've never learned it yet. There's another way. There's a formula for the inverse.
Doesn't D go up the top left and it becomes like negative? Like D and A become negative? Or is it B and C become negative? I know it's something that you flip. Yeah.
Technically, there should be a 1 over fraction in front of this, but it's 1 over the determinant. Which are negatives, which are positives? think that's right.
Yeah, that,
It's 1 over the determinant of A, and then you switch those two and minus signs on the other two. This is called the adjoint formula for the inverse. Okay, runaway scalded because this is too much linear. We can do all of this, by the way, directly. If I didn't know this idea about using row reductions, and I didn't know what to do, what I could do is I could say, okay, there's got to be some other matrix that when I multiply those two together, I get the identity. And then I set up 4 equations in the 4 variables E, F, G, and H. And I solve them in terms of A, B, C, and D. And it turns out that E isn't D, and I get this result out of it. Is it easy? Short? No. Does it work? Yeah. Does it suck? Yeah.
So I'm guessing that was the way that it was probably done historically first, right?
Yes. There's a large history to determinants. It's actually about 400 years of different papers. The only reason I know this is that there is a Math Association of America group that meets every summer and does history of something. And they do it in original sources. So they started with that Latin paper in 1200 when they did the history of determinants. And they looked at what Oersted did and what Wronski did, and all of these names that are big in linear algebra, and all of a sudden they got to what is the modern determinant about 1650 to 1750. But they worked their way through all of these papers and translated a bunch of stuff, and they were talking about it at a conference I was at. That's the only reason I know this. And that particular simultaneous equation version of it actually came after the adjoint formula, because adjoints were used in other ways to do other things. So the fact that we can circle back around and find the simultaneous equation version and make it, quote, easier, well, easy is a relative term.
It's rather remarkable, though.
It is. There are a lot of people responsible for a lot of different parts of this, but that shows up even here in group theory. The idea of looking at subgroup and subdiagrams and that whole behavior, a lot of it falls into like 5 people's laps. But if you really want to go back and look at why they were doing it, the reason we study groups, this is going to sound stupid, the reason we study groups is to solve equations better. And not just simultaneous equations, not matrix equations, but polynomial equations. One of the biggest questions, and this is the question going back 4,000 years, is how do you solve an equation? And if you asked me to solve 2x equals 5 4,000 years ago, I would say it couldn't be done. Because the Babylonian mathematicians only accepted whole answers. 5 over 2 isn't a number. So it took a lot to develop the theory of equations. And we get to here, and it turns out that groups, in particular permutations, are foundational to understanding how solutions to equations work. I promised to show you the beginnings of that by the end of the term. If I really wanted to get all the way to Abel's proof, it would take me through about section 50 of this text. I won't get there quickly.
Can we do number 5?
Sure.
The example 1 review.
As soon as I get a new piece of paper down here, you got a deal. Yes, hit me.
Show that H equals, and then it's like a fancy bracket. F is in the set of F with all real numbers.
Like that?
Yeah, and then it's like a straight version.
So that?
Yeah, so that F, the function of 0 equals F. And fancy bracket here. It is a subgroup of the group F of all real numbers of real value functions defined on real numbers under addition. Is it a field?
Somewhere in there's an operation. Does it say anything about the operation for FR?
Under addition.
Under addition. No, I didn't hear it. So, I'm in the same boat as I was with U4. I'm trying to show something as a subgroup. But this time I'm using addition. Then here, I wouldn't write a to a power. I'd write n times a. Because it's additive notation, but I'm not sure. It doesn't ask me about cyclic, so I'm not going to bother with that part. But I would if I were trying to do that here. Okay. Is this a subgroup? Remember, I only need 3 of the 4 to show a subgroup. Don't need associative, it's automatically inherited. So I need to show closure. I need to show the identity for the big group is in here. And I need to show that every element has an inverse. So those are the 3 criteria that I need to show for a subgroup. First one, closure. How am I going to do closure?
Do f of 0 plus f of 0 equals f of 1 plus f of 1.
Except that I need it to be 2 different functions, right? Because I need to take 2 functions in H, add them because my operation is addition, and show that it's still going to satisfy the property of being in H. So, let F1 and F2 be in H. Again, by our definition of the property of H, those 2 functions have the same value at 0 and 1. So F1 of 0 equals F1 of 1. And F2 of 0 equals F2 of 1. So F1 plus F2 of 0 equals F1 of 0 plus F2 of 0. Equals F1 of 1 plus F2 of 1 equals F1 plus F2 of 1. Therefore, F1 plus F2 is part of the set I wanted in the first place. It satisfies the condition for being in my set. We're closed. Two is about the identity. 3 is about inverses. So, 2. What is the identity function?
0 function.
The function that is 0 everywhere. So, the identity for the set of functions defined on R, we'll call that z of x is equal to 0 for all x. Does it satisfy the condition to be in our set. Because the value of that function at 0 is 0, and the value of that function at 1 is 0. Inverses. If I have a function in my set, what is the inverse of this function? That's if I'm multiplying, but my operation is,
Addition,
so what's my inverse under addition?
negative.
Subtraction, negative. Then minus f is the function I want to look at. And the question is this in H? I should write down. Minus f is the inverse. Wait a minute. F is in H. What do I know about f of 0 and f of 1?
Same output.
They're the same number. So f of 0 equals f of 1. Therefore, minus f of 0 is, and that means that minus f is in H. Closure, identity, inverses, they're all there.
Just back to the identity piece. So are we just assuming that z of 0 equals 0? Like, how can we do that?
Oh, no. That's, we're saying what function plays the role of identity.
Okay.
If I give you a function, I want you to add something to it that doesn't change it. What do you add?
0.
So I'm making the function that is equal to 0 everywhere. That's going to be my identity.
Okay.
That's the one that is the identity in the big group. Is it in H? Check. Yes. So I'm not inventing it out of whole cloth. I'm pulling it out of the way addition works. Oh, addition works. When I want to add, not change stuff, the only thing I can add is 0. Better?
Yeah.
More.
On the homework 4, can we do one of the, I forget what they're called, where you go across the set to find cycles? The cycles, yeah.
Oh, when I do the multiplication of cycles
Yeah.
sort of thing?
Yeah.
Because we did a bunch of stuff going across the find set. I thought that was orbit, and I was confused on which question. Which question are you actually asking me about?
So the number 12 on the homework, it's bracket, like just straight bracket, and then parentheses 1672 parentheses,
1672 parentheses.
then squared. Like there's like a square root, right?
Oh,
Or not
squared.
Yeah, squared, and then parentheses, and then 625. Or wait, actually, I might have written it down wrong. It's either I don't know if it has it written down. But
I've got my book.
Is the one we just got back?
yeah, because I
It
was
goes to,
trying to
Oh, I don't think I got that.
It goes to 4, 5, 2, 6
inverse it.
inverse.
4526 inverse. 4526 inverse, and then
And then 173. And then end the bracket. And then inverse the entire thing.
inverse the entire thing. Okay. It's supposed to work from the inside out. So I don't have to do anything to this. To do an inverse, I reverse the order of the numbers. So this 173 stays the same. This gets reversed. 6254. I got to square this. Oh, wait a minute. That's just doing it twice, right? 1672, 1672. let's do this first. Technically, I should go this way, right? If I want to do the whole thing at once, but I can do it associative property, right? And do whichever pair of multiplications I want to do first. I'm going to do this one first. So remember, we multiply right to left. So 1 goes to 6, 6 goes to 7. That means 1 goes to 7. 7 goes to 2, 2 goes back to 1. That's a closed pair. I've done 1 and 7. What happens to 6? 6 goes to 7, 7 goes to 2. So 6 goes to 2. 2 goes to 1, 1 goes to 6. That's a closed pair. So far, so good? Let's do the whole form.
Is there anything wrong with just leaving it expanded?
No? Well, what do you mean? Leave it like 162, you can absolutely do it that way. Sure. I'm going to go right to left across the whole thing. What happens to 1? But I keep going. Does anything happen to 7? Aha. So 1 goes to itself. That means it doesn't go in my parentheses. What happens to 2? Nothing. 2 goes to 5. What happens to 5? So 2 goes to 5. Now that's the start of a cycle, so now I need to pick up from 5. 5. 5 goes to 4. And nothing happens to that. What happens to 4? But then 6 goes to 2, so 4 ends up on 2. Close.
I did it by making them like 3 different functions. Kind of like, not 3 different functions, like I made like the tables.
Oh, yeah, the 2-row version.
Yeah.
That's fine.
Could you do that with 3 and then just work your way back up?
Yep.
Okay.
So when you did 2, you went from the right and you went from 2 in the 6, 2, 5, 4. But there's a 2 in the pairing of the 6, 2 there as well. How come we went to that 2? And
Because
not
I
this?
always work
Oh,
right.
It's because of that. Okay. And you don't have to like worry about that other 2 later then, like in the computation at all. You just
Well, not at this point.
right.
Let's see if I run into it again, right?
Right.
Because I've now dealt with 1, 2, 5, and 4.
And then when you start, like you started at 1, you always start at 1.
I can start wherever I want.
Okay.
I just know I'm going to start. I got to get up to number 7 eventually, right? So I might as well start at the bottom, work my way up. You want to start at the top, work your way down? It's not going to matter.
So if I got something different, when you get something different, if you started at a different number?
You might get these numbers in a slightly different order, but you would get equivalent cycles.
Okay.
You would get something that showed 2 goes to 5 and 5 goes to 4. If you get something that shows 2 goes to 4 and 4 goes to 5, that's different.
Okay, I was just confused. Let me know if I-
There were a couple of things about the way because I'm looking at what you finally wrote at the end, and I'm like, wait, that's backwards.
Yeah.
I did 1, I did 2, I did 4. What happens to 3? 3 goes to 1. Now I keep looking at 1. Oh, 1 goes to 7. So 3 goes to 7. Now I'm stuck on 7, so what happens to 7? 7 goes back to 3, and then nothing else happens to that. So I've now done 1, 2, 3, 4, 5, and 7. What happens to 6? 6 goes to 2, 2 goes back to 6. 6 is fixed. Now all of that is still inside the square brackets and inversed, right? What do I do when I do an inverse? I reverse the order. But this just says flip 3 and 7. If I wrote it flip 7 and 3, would that change anything? This says flip 2, 5, and 4. I do need to flip that one, so that becomes 4, 5, 2, or 2, 4, 5, or 5, 2, 4, as long as the order in which I'm doing the cycle part is the same. That 3-7 or 7-3. I could reverse them physically, but since they're disjoint, they don't have any numbers in common, it doesn't matter which order I write them. And yes, Reese, if you left it like this, instead of doing this multiplication first, then you just have to go across all 4 of those to do the multiplication. That's perfectly fine. Ben, better?
Yes, and I see, I didn't know that you could like, yeah, when you said you got to start on the right, I thought every time you finish a set, you have to start back. So like if you, like, you don't see, you have to hit every number, right? So that's why you can go in the middle.
Right, so if I start here, okay, I'm looking for 3. I see it, 3 goes to 1, 1 goes to 6, 6 goes to 7, so 3 has to go to 7. As long as I'm reading from right to left, I hit each number, I'm doing good. And yes, if I do it in 2-row notation, Noah, that's still perfectly fine. It just means that this 173 gets written 1, 2, 3, 4, 5, 6, 7, 7, 2, 1, 4 is left alone, 5 is left alone, 6 is left alone, 7 goes to 3. So there are a lot of extra numbers in there that I didn't necessarily get used, but I can then go, oh, 1 goes to 7. Now what happens?
And then at the end, I had to figure out like that.
The cycle version.
Yeah, the
Well,
cycle.
even if you'd written this, if you'd written 1, 1, 2 goes to 4, 3 goes to 7, 4 goes to 5, 5 goes to 2, 6 is fixed, 7 goes back to 3, right? So that's actually, you are absolutely correct writing this down. The only reason to use cycles is that they are physically less writing. If you like 2-row notation better, run with it. The dihedral group, the one with the shape, right, the triangle or the square, I know that's in the homework coming up, not in this one. I think it's in 6. But that is another case where writing the permutations in 2-row, as opposed to writing them as a product cycle, it's 6 one half dozen the other because we're only dealing with a small set. If I get larger and larger sets, then this is a lot easier to write than this, right? 173, if there were 14 numbers there, then 11 of them wouldn't move and it would be a pain in the neck to keep writing down. It's not wrong, it's just bigger. Better. More questions?
You just have another review.
Yep, hit me.
Find a generator for Z9 other than 1, and then find all generators for Z18.
So Z9 and Z18. Okay. I want a generator that isn't 1. And it says under addition? Or does it not say?
It just doesn't say.
Which means I'm assuming addition because Z and 9 goes with addition mod 9.
Yep.
So clearly 1 plus 1 is 2, 2 plus 1 is 3, gives me all of them, right?
Yep.
So pick something else.
2.
If I start with 2, the subgroup generated by 2, comma, keep adding 2.
4.
Keep going.
6.
Oh,
1.
I'm in Z9. What's next?
3. 5. 7. 0.
Is that the whole thing?
Yeah.
You did it.
Yeah.
Now, I picked 2. You picked 2 a chance, right?
Yeah.
What if you picked 3?
That
And that's all I get, right? 360.
isn't because like 2 and 9 are relatively prime.
So how do you answer the next question, which asks you for all possible generators of Z18?
Prime factorization.
Almost.
Find all the numbers that have greatest common divisor of 1 with 18.
I want the relatively prime ones. So I just need to look at all the numbers from 1 to 17. I don't need to look at 0, which would be 18, right? 0 only generates itself. But clearly, the greatest common divisor of 1 and 18 is 1. What about 2? 18 is even. 2 is gone, 4 is gone, 6 is gone, 8 is gone, 10 is gone, 12 is gone, 14 is gone, 16 is gone. They're all greatest common divisor of 2, at least. How about 3? Same question. That means 9 is gone as well. And 15 is gone as well. I would also cross out 6 and 12, but they've already been crossed out. So you can do it again if you really want to. 5?
They're relatively prime.
11. Oh, 7. Almost missed 7. 11, 13, 17. There are my generators. All of those numbers are relatively prime to 18. They're all generators.
Can you automatically eliminate composite numbers, or do you have to check?
I have to check that they have a common factor with my M here, right? I can eliminate only composite numbers that have a common factor. So I can eliminate 10 because it was even. But if I was in Z9, then 5 would work, 8 would work. The only factors are 3, right?
Yeah.
So it's a question of what are the prime factors, which is why when you said prime factors, I'm like, that's really close. I need to know what the prime factors are of this, and then I eliminate all of the things who share a common factor other than 1. Hey, there are 6 of them. There are 6 generators here. Counting generators is going to be an interesting exercise. There are 6 generators for Z9. We did this for Z9. The only numbers we throw out are 3 and 6. There's 6 generators in both cases.
Just because they're multiples of each other. So like if you add, like we're going from 9 to 18, you would eliminate all the evens, because that's like times 2 is 18. You multiple of 2 would not be 1.
I think there's more to it than that. Because what happens if you look at 27? There's way more generators for Z27. So there's something about what's going on in the relationship between the primes and the numbers that are relatively prime underneath it. That's actually a really interesting question. I promise we'll get to it a little bit later. It's coming up. Euler talked about this one. It's one of his. Want to know a little bit more in advance? You can look up the Euler phi function. That's a lowercase phi. We'll get there. We're not there yet. Not that far away, but it's coming. Better?
Yeah.
Right. More.
So I was going to ask, the 6 goes, like the 6 end up being, it's saying find the subgroup generated by 14 in Z23 is supposed to be like really long and a lot of.
The subgroup generated by 14 in Z23.
Yeah,
Oh, yeah, wait a second. The subgroup generated by 14 in Z23. What's greatest common divisor of 14 and 23? So it's going to be all 23 of them.
that makes no sense.
So if it's like that, we just list all.
As long as you remember that fact.
Yeah. So
Oh,
there's no
wait, this is
particular-
relatively prime. It generates the whole group. I'm done.
And then the part two, that where it's like Z3, you have to actually like go through it and do the cycle.
What was the part B?
How about like use 14 as generator?
Yeah, what about
Z30?
Well, then the greatest common divisor is 2, right?
So it'd just be the evens.
So I should get half as many,
Oh.
right? In Z30, there are 30 things. The greatest common divisor is 2. I should get 15 of them. I don't know that they're all evens because I got a 15. Will I just get the evens? Using 14. I should get all the evens. I know I won't get them in a normal order, will I? I'll get 14 and 28, and then 28, 14 is 42, so I'll get 12. I'm going to bounce around a little. I think I should only get the even ones, but it's not obvious.
We just do it.
Sure. I got time. Okay, so I start with 14. 14 and 14 is 28. 28 and 14 is 42. Mod 30, that's 12. 12 and 14 is 26. 26 and 14 is 40, but I'm in mod 30, so I get 10. 10 and 14 is 24. 24 and 14 is 38, mod 30. 8 and 14 is 22. 22 and 14 is 36. 6 and 14 is 20. 20 and 14 is 34. 34 and 14 is 18. 18 and 14 is 32. 2 and 14 is 16. 16 and 14 is 30. Yes, I got all the even numbers. But notice I got them in a very weird order. How could you prove that you're going to get the same thing as if you started with 2? We actually stated that as a theorem. We said that the subgroup generated by S is equal to the subgroup generated by R if and only if the greatest common divisor of S and M is the same as the greatest common divisor of R and M. So once you know the greatest common divisor of 14 and 30 is 2, you could use 2. And then you'd only get the even numbers, right? I think it's very interesting, though, visually. Here is an artistic challenge for you. There are lots of numbers whose greatest common divisor with 30 is 2. 14 and 2 are just 2 of them, right? 4 is in there as well, right? No, 4 is at its own base. 4. It's also greatest common divisor is 2, right? So what I could do is I could write the numbers from 0 to 30 in a circle and connect the numbers in this order. Take a picture. Right? You'd get some star with 30 points, wouldn't you? Do it for 2. And you get a 15-sided polygon. Do it for 14, you're gonna get stuff that crosses itself a bunch of times. Do it for 4, you're gonna get stuff that bounces around differently. How many different stars can you make out of this? Vihart is a YouTube mathematician artist, and she did an entire video. It's only about a 15-20 minute video on star patterns. She didn't do it in terms of group theory, but it's in there.
So is that similar to how like fractal patterns are generated eventually? Is it
Um,
similar maths?
No, because fractal patterns use a different kind of deterministic algorithm.
Oh,
Because this is a discrete algorithm and most fractal imagery algorithms are discrete based, the self-similarity comes up from a different reaction. There's something called iterated function systems, IFS, and Michael Barnsley did a lot of work on those back in the 80s and 90s. There's a bunch of stuff in his books as well if you want to look up him for IFS work. Michael Barnsley, IFS. That is not my preferred approach to fractals because I did it through complex numbers, but there's a lot of interesting crap there. And that's geometrically based, which is why the star patterns come into play. Okay, people, if I still have your homework and you still need to give me homework, come do that. Otherwise, we'll see you all on Tuesday when we will turn in the last thing and then the exam is Thursday.
Good weekend.
You as well.